today we're going to be talking about something called a logistic curve. Before we do that, let's remember about exponential growth. So exponential growth is modeled with the differential equation dp dt equals kp, where the rate that this is growing is directly proportional to the actual population. We discovered that the general solution is ce to the kt. Okay, so let's look at this scenario here. In an experiment involving the spread of disease, one infected mouse is placed in a group of 99 healthy mice. The maximum daily growth rate of the disease is 10%. The rate of change of the number of infected mice with respect to time t in days follows what's called a logistic model. Okay, so the equation p of t equals 100 over 1 plus 99 e to the negative 0.1 t models the number of infected mice with respect to time in days. So we're going to graph this equation. Okay, so I have here the equation in my y1. For my window, for right now, and I'm going to change this in a minute, I'm going from -1 to 50 in the x direction. In the y direction, if there's only 100 mice in this thing, that's going to be a maximum, right? Because we can't infect more than 100 mice. Okay, so if I graph this, what does it look like? Looks kind of exponential, right? Well, if I change my window to go out to 100, there's exponential, right? Oh, but then it levels off. Well, let's think about this situation. It is going to grow exponential at first because this mice is going to start infecting all the mice around him. But as more and more mice are infected, less are available to get infected. And we are going to reach this maximum of 100. We're not going to be able to go past that number. So the first observation I'm going to write down here is that it starts exponential, but then levels off. The second one that I'm going to write down here is that this graph has two horizontal asymptotes. It has a horizontal asymptote at 0, because we're never going to get less than 0, and it's going to have a horizontal asymptote at 100, because it's never going to go above 100. So horizontal asymptotes at y equals 0 and y equals 100. Okay, the differential equation for the situation dp dt equals this thing here. And if we solved this differential equation, this is what you would end up with. Okay, so let's look at two scenarios. So if p is very small, what is this going to look like? So dp dt is equal to 0.1 p 1 minus p over 100. Okay, well, if p is very, very small, this is basically going to be 0. So what you're going to end up with is just dp dt equals 0.1 p, which is going to be an exponential one, just like up here. So when p is very small, the rate of change is exponential. But then as this becomes bigger than 0, that changes. So what happens is p gets really close to 100. Okay, well, as p goes to 100, then this goes to 1. Okay, which means we have 1 minus 1, which means we have 0 here, which means our growth is going to go to 0. And that's the rate of change, and that's why it's going to level off, is because the rate of change is now essentially 0. So this is the idea behind a logistic curve. So let's look at some of the information and how that fit into the differential equation and ultimately the solution. So the 100, so if we have 1 mice and we've dropped them in with 99, we have a total of 100. So that's where this value is coming from in the differential equation, and that's where this value is coming from in the logistic equation. The 10% growth rate is going to be this value in front of the P here, and this value in front of the T here. This 99 comes from the initial condition, but it doesn't always necessarily equal the 99, and we'll see that when we do the differential equation. Okay, so this is the general logistic differential equation. dp dt equals kp 1 minus p over m. You can also see this written as dp dt. If I factor out a 1 over m, if I factor out a 1 over m, then this would be m minus p. So multiply this back through, this would become 1, this would become p over m. So the important parts here, k is the maximum population growth rate. Okay, m, okay, this value here in the previous problem, it was that 100, the total amount. We call that the carrying capacity. Okay, it's going to be the absolute limit of whatever the situation we're looking at. All right, so now we're going to solve this differential equation in general. Okay, keep in mind that k and m are just constants. P is our variable. So before I separate my variables, the first thing I'm going to do is pull out this 1 over m. Now before I go any further, notice that we have a whole lot of white space here. This derivation is going to take up quite a lot of space. It's very long, but we only have to do it once, because once we have the general solution, we're good. So you might just want to watch as I go through this and then copy it down later. That's up to you. Okay, so my next step is to separate my variables. So dp, so on this side I'm going to have the p and the m minus p. That's going to equal k over m dt. Okay, we want to integrate this. Okay, if we look at this integration, we have 2 factors. So what we're going to use here is partial fractions. Okay, so off to the side, I'm going to rewrite this . Okay, so that's going to equal some number over p plus some other number over m minus p. All right, so my equation, to get a common denominator, that means 1 is going to equal a times m minus p plus p times b. Okay, so then we pick our convenient values of p in this case. So I'm going to let p equal, to get rid of this one, I'm going to let p equal m. And I know this is a little bit weird since we're dealing with letters and not numbers, but it all works out the same. So 1 is going to equal, this is going to go away because m minus m is 0. So we're going to have b times m. We're solving for b, so b is going to equal 1 over m. Okay, we've got b. Now to get a, I'm going to let p equal 0. That means 1 is going to equal m minus 0. So we're going to have a times m, and then that goes away, which means a is also 1 over m. So we're going to use that back here. I'm going to separate this out. So this is now going to be the integral of 1 over m over p plus 1 over m minus p. All right, now we're going to integrate. This one is going to be 1 over m times the natural log of the absolute value of p. This one is also going to be the natural log, but when I integrate, we're going to have this minus here. So we're going to have minus 1 over m natural log m minus p. And again, this would be plus, but because of the negative p, we include that. On this side of the equation, we're going to have k over m times t. All right, our next task here is to solve for p. I have two p's, one here and one here. I need to consolidate them. Okay, so what I'm going to do first is multiply both sides of this equation by m. Actually, before I do that, I'm going to factor the m out. Okay, and I'm going to make this a minus, and I'm going to show you why in a second. That's going to make this a negative natural log of p plus natural log m minus p. Okay, I'm going to multiply by a negative m. So on this side, that's going to go away. On this side, this is going to be negative kt. Over here, we have a minus log and a positive log. If we have just the plus, we can multiply the insides. With the minus, though, we're going to use division. So the reason I made this one the negative is that puts just one thing in the denominator and not two things, and that makes our life simpler. So this is going to be the natural log of m minus p over p. And I realized I forgot in this step. Plus c. That was bad. Okay, so now what? Hey, we're going to raise both sides to the e. So this is now going to be m minus p over p. This side is going to be c e to the negative kt. Okay, we've done that a lot. Now I'm going to divide this by p and this by p. So we're going to have m over p minus p over p is 1. Okay, so I'll add that 1 over. Actually, let me go back up a step here. Okay. In this step here, or really this step here, when t equals 0, if I make this t equals 0, then m minus p over p is going to equal c. Okay, because we're going to eventually need to solve for c. So this is actually my initial condition, and we're going to call that a. So I'm going to make that an a. Okay, so I'm going to add the 1 over. So m over p is going to be 1 plus a e to the negative kt. I'm going to flip this over. So p over m is going to equal 1 over 1 plus a e to the negative kt. Multiply over by m, so p is m 1 plus a e to the negative kt. So this is the general solution. So our general solution to the above differential equation is p equals m 1 plus a e to the negative kt. P of t, so P is going to be the population at any time t. M is our carrying capacity, just like it was in the differential equation. Okay, K is again our max population growth. Okay, and if P of 0 equals some value P naught, or initial condition, then A is going to be M minus P naught over P naught. Now you can remember this one, or you can plug in a 0 and solve algebraically for the value of A. That's perfectly acceptable. You'll end up with this when you do that. Some properties. Just like we're just describing the differential equation. So the horizontal asymptote at y equals 0 and y equals m. Okay, on the graph, let me go back to our previous graph. This graph is always going to look like this, where it's going to be concave up and then it's going to be concave down. There's a point in here where the rate is at its maximum, and that's also the point of inflection. Okay, so the other property is that the inflection point and it's always going to occur at half of the carrying capacity. Okay, once half of the population, so in this case the mice, get infected, then the rate starts to slow because there's just less mice to infect. That's also where the max rate of growth occurs. All right, so let's do some examples. All right, here's where we usually do a rumor spreading through a crowd, but we're going to modernize this here. A tweet from Twitter account spreads through a town's Twitter users in a proportion of the product of the number of people, P of T, who have heard it and who have not. And whenever you see that product, that's telling you it's logistic. Suppose the rate of the distribution of the tweet is 0.4, and the original amount who know it is 100. If P equals PT is the number of people who receive the tweet, and there are 7,500 Twitter users in town, we're going to write the differential equation. So the general differential equation for a logistic curve, anything in this scenario, is going to be the rate, which is going to be 0.4, P, and then 1 minus P over the max population. Okay, so we only care about two numbers in the differential equation. In the logistic equation, the new piece, so let me write the general solution down first. Okay, K is still going to be 0.4, and M is still going to be 7,500. The A is going to be the max population, or the carrying capacity, minus the initial over the initial, which in this case is going to be 74. Okay, if you didn't know that, what you'd end up with is you'd have M, you'd have your K, but you just plug in a 0 here, and you plug in your max population here. When you solve it, this is the equation you're going to get. So you don't have to have this memorized. Right, so our general solution, we don't have to sit here and break this down and do all of that stuff. We now know what the solution is. So my M is that, my A is 74, e to the negative K is 0.4, T. Okay, what is the value of P when it's spreading at its greatest? That's always going to be the max over 2, which in this case is 3,750. Okay, it says find the time it takes for 80% to receive this tweet. So 80% of 7,500 is 600, or 6,000. Now you can solve this algebraically. It's a bit of work to do it, but it's just involving natural logs and everything. But if you're going to have to involve a natural log, you're going to have a calculator. So I'm just going to go ahead and graph this. So in my y equals, I put the graph, or the logistic equation, 6,000, because that's what I wanted to equal. For my window, I went from 0 to 50, but you might need to change that depending on the rate. And then from 0 to 7,500. So my graph looks like this. So we have that nice logistic curve. We're interested in that. So I calculate the intersection. Okay, and we get a value of 14.226. And that would be in hours. All right, so a 2,000-gallon tank can support no more than 150 guppies. 6 guppies are introduced into the tank. Assume the growth rate of the population is this differential equation here. Okay, notice that this isn't P over a value. We've got this 150 here. So this is going to look like the general equation K over M P M minus P. Okay, so we're going to find the formula. So we need to figure out what K is. We know that M is going to be 150. Our K is going to be, well, K over M, which is 150, is going to equal 0.0015. So to solve for the K, we're just going to multiply. So my K is going to be 0.225. And then my A is the maximum 150 minus the initial amount, which is 6, over that initial amount, 6. Okay, so now we have all our parts. So my population is going to be 150 over 1 plus 24 e to the negative 0.225t. Okay, how long will it take for the population to equal 100? So we set it equal to 100. And I would again graph it and find the intersection, because it's easier than doing the algebra. Okay, and we get 17.05. For what value is the population growing most rapidly? Well, that's going to be at the maximum population divided by 2, which is 75. And then the last question, what are the asymptotes? That's going to be at y equals 0, or I guess p equals 0, and at 150. Okay, suppose the growth of a population is given by that logistic equation here. So what is the population at time 0? Well, if I plug in a 0 here, I'm going to have 1,000 over 1 plus 999 e to the 0. So that's just going to be 1. So we're going to have 1,000 over 1,000, which is 1. What is the carrying capacity? Is 1,000. Now, I bet you're wondering how a population of 1 grows. I'm wondering. But sure, why not? So when does it equal 75% of capacity? So just that same setup, and then I would graph it. And if you need help with the graphing, let me know. But just set your window so that you can see the max capacity and then some amount of time. And if you need to adjust the time to see the intersection, that's easy enough to do. Okay, the population P of t is of a species satisfies the logistic equation here, where the initial population is 3,000 and t is in time years. So what is the limit as x goes to infinity? Well, that means we're looking for the carrying capacity. Now you might be tempted to say 5,000, because that's what that denominator is here. But this is 2, not 1. This must be 1. So what I need to do is factor that 2 out. Sorry, factor a 2 out. So we're dividing everything by 2. So we're going to have 1 minus this becomes P over 10,000. So my limit, or my carrying capacity, is going to be 10,000. Okay, this next one, which could be the logistic growth. So we have all these different differential equations. The first thing I'm going to do is cross off the ones that don't really fit the format. I'm going to factor a P out, and more specifically this entire thing, so I can get the 1 minus. So I'm really left with 2 candidates, so I'll just factor the 0.2p out, which is going to leave me with 1 minus. If you divide this by 0.2, you're going to get 0.005. Okay, well, is this the right number or not? If you turn this into a fraction, this is going to be 1 over 200, which is what I'm looking for, since that's 200. This one, you're not going to get the same value. So those are logistic equations. AP really does these types of equations where you're just trying to interpret them. You won't have to derive the logistic equation ever again, just understanding what the different parts are.